Hello everyone, I am Alvi Ataur Khalil. I am going to present our work titled FedUp, Federated Deep Reinforcement Learning Based UAV Path Planning Against Hostile Defense Systems. The authors are myself and Dr. Muhammad Ashikur Rahman. Both of the authors are from Florida International University. To give a brief overview of the presentation, first I will be talking about the motivation behind this work. Then I will be talking about the contributions that we made. Then I will discuss the background information, followed by the framework that we proposed. Then I will talk about the SRMB module through which we improved the deep reinforcement learning. Then I will talk about a simulated environment. Then I will talk about the performance evaluation. Finally, I will explain the experimental analysis, and I will conclude the presentation by the discussion on future work. So, in military operations, unmanned aerial vehicles (UAVs) have been heavily utilized in recent years. However, due to the antenna installment regulations, UAVs cannot be controlled by human operators in restricted areas. Hence, artificial intelligence AI-driven UAVs are the practical solution to this out-of-coverage problem. With the increased use of autonomous UAVs in military applications, defense systems are deployed to target and shut down the enemy UAVs in operation. Thus, UAVs are needed to be trained not only to achieve goals but also to avoid static and dynamic hostile defense systems. The contributions that we made through this work: we designed and implement FedUp, a federated deep reinforcement learning based novel UAV path planning framework, enabling UAVs to carry out missions in a hostile environment with true dynamic defense systems. We introduced significant replay memory buffer SRMB module for selective training of FedUp to quicken the training process by selecting the crucial experiences during the training. We evaluate the proposed FedUp framework with respect to goal completion, obstacle avoidance, and travel distance. The evaluation results validate that FedUp performs better than standard DRL, especially in dynamic hostile environments. Now, I will talk about some background information that will help explain the framework. A promising method for autonomously learning complicated behaviors from limited sensor observation is deep reinforcement learning. Although a significant portion of DRL research has concentrated on video game application and simulated control, DRL has also shown promise in making it possible for physical robots to learn complex skills in real world. Unlike the basic reinforcement learning where an agent manages a Q table, DRL agents maintains a neural network called Q network as a learning mechanism. For training the Q network, the agent's experiences are saved as training data samples into the storage called replay memory buffer. To provide stability to the action decision from the Q network, an additional supplemental neural network is added to the DRL framework called the target network. The weights from the Q network are copied to the target network after a certain number of episode steps. The target network predicts the future Q values for the next states, which are used to calculate the loss of the Q network's prediction. Now I will talk about the federated learning. Data and computation resources are now often dispersed across n devices, different areas, and corporations. Laws or regulations prevent the aggregation or detect sharing of distributed data and computing resources among various areas or organizations for the machine learning tasks. Federated learning is an effective approach for utilizing distributed computing and data resources to collaboratively train machine learning models. FL also abides by the rules and regulations to ensure data security and privacy. The primary goal of FL is to do a collaborative on-device training of a single machine learning model without disclosing the raw training data to any other parties. The basic steps of an FL architecture is presented here, where the cloud server holds the global machine learning model to be trained. In the first iteration, the random weights of the global model is sent to the n devices, each having a local model. The n devices train their respective local models with their private data, and then submit the local model's weights to the global model. Finally, the global model aggregates the weights and updates its weights. The updated global model's weights again sent to the end devices, each of which updates their local models and trains it with the private local data. These steps are repeated till the end of iterations. Here we talk about the framework. Since we consider that a collaborating swarm of UAVs deployed in the same environment together will simultaneously explore different states of the environment, we utilize the vertical federated reinforcement learning concept. Each UAV agents will be deployed at a different state in the three-dimensional environment, and they will interact and explore the surrounding states. Each of the UAV agents will have its own local reinforcement learning model, which will be trained through k consecutive episodes. The observation vector size is exactly the same for all the agents, and so is the action space. At the end of each episode, the local queue network of an agent is trained with a random batch of experience samples from the memory buffer of the agent. The queue network will be consulted for an agent's exploitation action. Finally, at the end of each K episode, the UV agents will submit the current weights of the respective queue network to the vertical federated DRL module, VFDRL, where an aggregator module performs the weights and biases aggregation from all the local models. At the beginning of next K plus 1 episode, the local RL model are reinitialized to replicate the global federated model. The structure of the global model is exactly identical to local models. The vertical nature of the FL drives the exploration faster. This accelerates the training process of the global model and helps in further improving the model's performance in relatively less number of episodes. In this work, we additionally propose SRMB, that is Significant Replay Memory Buffer, to further improve the learning process of DRL. Generally, in case of DRL, for each time step, the agent's current state, action, reward, next state, completion flag indicating goal completion state are stored into a memory buffer as a single tuple. The replay memory buffer has predefined memory size. As an episode terminates, a random batch of tuples are selected from the memory buffer to train the queue network. However, this randomization can hardly ensure that queue network is served with the memory samples that will aid the learning of intelligent behavior. We propose SRMB, which will help to train the model in a controllable manner by storing the most significant memory tuples. Each agent will have both replay memory buffer and SRMB, where the sampling rate technique with the parameter sampling rate sigma and sorter with the parameter sorting phi will control the effect of SRMB. So let's talk about the first module, sorter. Unlike the general DRL, where the replay memory buffer directly receives the memory tuples, in our case, the sorter receives all the memories. Then it sorts the memories into SRMB according to the phi parameter. Whichever memories are not stored in SRMB are sent to the replay memory buffer for storing. The value of phi parameter is set from 0 to 1, where a 0 value means only the experiences for an agent ends up on a goal or obstacle are stored in the SRMB, while none of the layers encounters are considered significant. The next one is the sampling technique. This module is responsible for preparing the batch samples for queue network training. According to the sampling rate parameter, this module takes B into sigma samples from SRMB, where B is the size of a single training batch. Consequently, the rest B into 1 minus sigma samples are taken from the replay memory buffer. Sigma parameter controls the sampling rate of the experience memories which are selected for batch or training of the queue network. This parameter can take value from 0 to 1, where 0 means all the samples for the training batch are taken from the general memory buffer, and 1 means all the samples for the training batch are taken from the SRMB. For the simulated environment, we introduce 3 types of defense systems. First one is the static defense system. These defense systems are simulated by designing static towers with different heights at different locations in the environment. The blue towers in these figures are the static defense systems. Then the second one is the dynamic fixed route defense system. These defense systems are simulated by objects moving back and forth in the environment in a fixed route. There are three kinds of routes: horizontal movement with variable x-axis values, horizontal movement with variable y-axis values, and vertical movement with variable z-axis values. All the other axes for all the three cases are kept constant. This defense system resembles the guarding UAVs. These are shown in the figure by the red spheres. The third one is a dynamic stochastic defense system. These defense systems are simulated by objects moving randomly in the environment without any fixed route or path. This defense system resembles surveying and exploring UAVs. These are also represented by the red spheres, and only the green spheres that are shown in the figures are the goals. So the UAVs are initialized at a location, at an edge or location of the simulated environment, and they have to avoid collision with these obstacles and reach the goals. Now we'll talk about the performance evaluation of the model. Here we show the goal completion capability in different hostile setup. The GCP here means the average goal completion percentage from 50 iterations by the UAV swarms with DRL, SRMB DRL, and FedUp. From the first figure, it is seen that with only static obstacles, all the techniques perform almost similarly. However, as the dynamic obstacles are introduced in the environment in the figure 2 and 3, there arise visible performance difference among the methods. Although the average GCP goes down with all the methods, FedUp performs substantially better than SRMB DRL and DRL, completing around 80% goals. The SRMB DRL technique, even without federated learning, does perform better than the standard DRL, completing around 60% goal in the dynamic environments. Here we talk about the average distance traveled in different hostile environments. Ideally, the less the distance traveled, the better the model is. So ADT here means the average distance traveled, and these evaluations are done with DRL, SRMB DRL, and FedUp after 500 training episodes, 1000 and 2000 training episodes. So in the first figure with 500 training episodes, it is observed that FedUp agents require minimal distance to be traveled to complete the goal set in every kind of hostile setup. In the second figure, after 1000 training episodes, we observe a fast improvement of FedUp method, while the other technique improve linearly. Finally, in the last figure, we see SRMB DRL improve the most and gets close to the performance of FedUp around 25k 3D gates, while there is little improvement in the latter. This is because the training performance of FedUp with respect to ADT becomes saturated after 1000 episodes. Even after 2000 episodes, there is minimal improvement observed for the standard DRL. Here we evaluate the obstacle avoidance capability in different hostile setups. The OEC means average obstacle encounter count, and these are performed after 50 iterations by UAV swarm with DRL, SRMB DRL, and FedUp. So with only static defense system, FedUp performed substantially better than both DRL and SRMB DRL as presented in the first figure. However, as dynamic obstacles are introduced in the environment in the later two figures, the performance of SRMB DRL becomes comparable to FedUp. This is because both the technique utilize SRMB, while the slight advantage of FedUp comes from the federated DRL module. The overall performance of both methods degrades with a tougher hostile environment. Finally, here we perform experiment with the parameters of SRMB for determining the optimal value of phi and sigma. In the first figure, the average GCP for the agents with variable sigma parameter values are experimented with phi being set to 1. In the second figure, average OEC for the agents with variable sigma values and the phi values set to 1. And finally, in the last figure, the average GCP for agents with variable phi parameter values with sigma being set to 0.7, and those are done for 50 iterations. In figure 1, we observed that when all the significant experiences are ignored in the training phase, that means sigma being set to 0, there is no improvement in GCP, as the agents do not know what goals and obstacles are. As we increase values, we see better performance with respect to GCP. However, setting the sigma to 1 incurs some random behavior, as the agent only know the significant situation and do not know what to do when no goals and obstacles are around. we found that the optimal value of sigma is around 0.7 with respect to GCP performance, and that is the maximum average GCP. In the second figure, we observe similar behavior for zero value of sigma, as the agents do not know what an obstacle is. However, setting it to 1 in this case causes the OAC to decrease to 0 really quickly. This is because the agent is trained very well about what to do when obstacle is around. In the final figure, we experiment with the phi value and observe a linear improvement of performance with respect to GCP. This is quite obvious, as more observable layers will help the agent to act better when goals are in surrounding areas. The evaluation results have shown that the proposed FedUp model outperforms the standard DRL method in both simplistic environment with only static defense and the complex environment setup with dynamic defense. We observed that the proposed model training is remarkably faster than DRL in terms of training episodes. There is a significant improvement in performance in terms of obstacle avoidance, 68% less OEC with dynamic defense, goal completion, 113% greater GCP with dynamic defense, and minimizing the travel distance, that is 57% less ADT with dynamic defense. In our future work, we will focus on further optimizing the SRMB and VF-DRL modules and experiment with even more sophisticated defense systems, including the tracker and follower UAVs. Thank you for listening to my presentation. If there's any question, I'll be more than happy to answer.